Hi there. So my name is Dr. AJ Kumar, PhD. It looks like I am recording with the correct microphone. So this is a bit of a diversion. It doesn't really fit into WFC, and you can skip this video without any loss in continuity. But I wanted to tell you the typical mathematician's perspective on set theory and Boolean algebra. And this is the way a typical mathematician will think about this subject, which is a lot different than the way we're going to think about it. So from a typical mathematician's perspective, algebra is sort of a thing you do in order to do set theory. Is just the sort of formal logic that underpins set theory. Set theory is typically what you deal with as a mathematician, and I'm going to give an example. Sets, these are the typical way mathematicians interact with Boolean algebra. They are one level of abstraction above Boolean algebra. So a set is a unordered collection of things. So, for instance, in traditional mathematics, the set 1, 2, 3, this is no different from, let's say, the set 1, 1, 2, 1, 3, 2. So repetition doesn't matter and order doesn't matter. All that matters is whether or not you're an element of the set. And typically in mathematics, the traditional way you think about the foundations is through these infinite sets. And if you're if you're watching this, you're coming from Weilberger, and he, I think, correctly has identified this reliance on infinite processes and infinite sets as a logical stumbling block and actually a mistake that mathematics made roughly about a century and a half ago now, that really makes the subject a lot more complicated than it needs to be. However, I am going to try to give the traditional perspective so that you have some context for why it's important that we talk about this. So, one reason that we're going to talk about sets is it provides a convenient means of visualizing these operations that we're going to talk about. So the typical story is that you have three primitive operations. So number one is called the union, which is, if you view it as a Venn diagram, it's the inclusive OR. It's everything in both. So the way you write this is A union B is defined as the set of all x such that x is in A, inclusive OR x is in B. The next one is called the intersection, and it's the middle part of the Venn diagram. A intersect B is the set of all x such that x is in A and x is in B. And the third one is something called the complement, which in set theory, I don't think there's some problems you can run into with this. Look up Russell's paradox if you want an example. But most mathematicians sort of view this subject naively and don't really, and sort of just sweep the sort of logical issues under the rug. And if you, Munker's book called Topology, the first chapter of it gives a really good, honest, thorough breakdown that is very honest about the typical way an average mathematician thinks about these things. But anyway, you have some universe that's implied, and A complement, which is denoted as A superscript C, is defined as the set of all x such that x is not an A, or not x in A. All right, and so I'm going to give you an in-context example from Topology. And this is, take this with a grain of salt. There are kind of logical, what Weilberger would call logical difficulties with the field of topology that make it way harder than it needs to be based on the way it's set up, but this is the way that it's set up, and if you read a topology textbook, this is what you're going to see. So given a set X, a topology, that's a keyword, which is why it's highlighted, on X is the set T, is a set T with this curly T of subsets of X that has the following properties. These subsets in the T, these sets in the topology are called open sets. And this is going to be abstract, and it's not important that you understand what this means, but it is important that you are able to follow the chain of reasoning. Okay, number one, the empty set is in the topology. Number two, the whole set is in the topology. Number three, if you have an arbitrary subset of the topology, so by that it can be finite, countable, or uncountable. So we're talking about stacking infinite sets of an infinite set of infinite subsets of an infinite set. So there's a lot of, already you're stacking infinite on top of infinite, which is where you run into problems trying to do mathematics, trying to actually compute things in math. Anyway, if this collection U alpha is an arbitrary collection of open sets, so sets in the topology. That's why I wrote the subscript operator, or subset operator, and in in a couple videos, probably the next video, I'm going to explain precisely what this subset relationship means, but we're going to have a different point of view on set theory. Then the union over alpha of U alpha, so just the set of points that are in at least one of these U alphas. That's what this symbol means. So it's in at least one of these U alphas. That's in the topology. Now, actually computing this set is literally impossible in general, and that's because you're having to do an infinite number of operations. You have to check an infinite number of conditions, and maybe one of them will be true, maybe one of them won't. Okay, and the fourth condition is that if you have a finite collection of open sets, then their intersection is in the topology. So in other words, if you have any arbitrary collection of open sets, you take their union, that's itself an open set. If you have a finite number of them and you take their intersection, that is also an open set. Okay, and then there's something called De Morgan's laws, which is if you flip union and intersection in these two laws. So something called a closed set is a set whose complement is an open set. So X, where the implied universe is X. And then De Morgan's laws say that the complement of a union is the intersection of the complements, and the complement of an intersection is the union of the complement. I might have that wrong. Go look up De Morgan's law. We can prove those later. I'm just trying to give you an in-context example for why an average the way an average mathematician thinks about this. Okay, so again, a topology is a set of subsets of a set which contains the empty set. The whole set is closed under arbitrary unions and finite intersections. Okay. Definition. So if x, tx, so this pair, and y, ty are two topological spaces. This should be in yellow. Where's my pen? Oops. Topological spaces should be in yellow. Then a function f from x to y, again, Weilberger has some issue with the concept of a function, which I actually don't understand, but putting that aside, this function is continuous precisely when, for all u sub y in the topology of y, so for all open sets in y, this is called the preimage. So the preimage under f of u sub y is defined as the set of all x in x such that f of x is in uy. So this is all, so we're picking some open set in y and finding all of the points in x that map down to uy. So maybe let me draw a picture. I'm not going to draw a picture. I should draw a picture. I don't want to draw a picture, but this is important. So we have, let me draw a bigger picture. We have our space x, our space y, and our little subset uy. This is an open set in y. And ux, maybe it's a disjoint pair of subsets, so maybe it's a many to one map. And these are the set of things that map to uy. So the set of things in x that map down to u sub y. This is called the preimage of u sub y under the map f. Okay? This has to be an open set in x. If that is true for every u sub y, which is an open set in y, then then the function f is continuous. That is the definition of a continuous function. And in the special case where you have the normal topology on Rn, then you get the epsilon delta definition. And so the sentence to remember, the preimage of every open set is open. And so, funny thing, take your math professor and ask them to write down the epsilon delta definition of continuity. What they're going to, maybe not an applied mathematician, a pure mathematician, will remember the preimage of every open set is open, and they'll just use that to reverse engineer the epsilon delta definition, and usually they will screw it up. They'll start to write it backwards and go, oh, no, you actually need the epsilon first, right? So you need the u sub y first, and then to get the u sub delta. Anyway, that's a fun exercise. Try that, because this is the way an average a pure mathematician who's been exposed to topology, they're going to remember this definition because it's a lot. This is a sentence. You can remember a sentence a lot better than some symbol nonsense. So let's use this set theory idea to just prove a very simple theorem. That if you have three topological spaces like this, and you have a function from the first to the second and the second to the third, and you compose them, then the composition is continuous. So in other words, if you compose two continuous functions, the composition is continuous. So for a proof, we're going to pick some open set u sub c in the topology on C. That's what this first one is. So pick an open set here, trace it back to B, so take the preimage under G. Okay, well, that preimage in the topology of B is going to be open, so it's going to be in the topology of B, and that's because G is continuous. So we take some open set here, pull it back to get some open set here. Okay, and then we're going to pull this one back over here to get an open set in A. Okay, and this is open because F is continuous. Okay, and then, well, doing this double pullback thing, that is, so F inverse of G inverse of U sub C is equal to G of F inverse of U sub C, because it is. And so therefore, G of F has the property that the preimage of open sets is open, so therefore it is continuous. This is kind of a diversion from the main thread of WFC, but I wanted to point out this is kind of why it's important to iron out these foundations, because something as basic as if you compose two continuous functions, the outcome is continuous. That result, the typical way a mathematician thinks about it is through this, a pure mathematician at least, the typical way a pure mathematician views this result is through this framework of infinite set theory, which I don't think is as logically strong as mathematicians would like to admit. And I think Wildberger is right about that, but I'm not necessarily committed to that position. Notice that this doesn't really involve the complement, or the, well, oh, you know what, it does involve the complement, because I mentioned that if you take the complement of an intersection, you get a bunch of unions. And then if you take a complement of a union, you get a bunch of intersections. That's called, I think those are called De Morgan's laws. So, yeah, in summary, just showing you an in-context example of why ironing out set theory is important. All right. Next video, I'm going to actually talk about something that is more directly relevant to WFC, but I wanted to, yeah, okay, I'm repeating myself. Thank you for watching. See you in the next video.